All right, here we go. Inverse functions. Suppose we had a set of ordered pairs, f of x, or some set of ordered pairs, f, I should say, is 1, 4, 2, 5, and 3, 6. And remember squiggle brackets, the way of writing a list. This list is called f. What would f inverse be? Why? Why obviously, though? Oh, did you say obviously or opposite? Opposite. What do you mean opposite?
Like all the x's to the y's and y's to the x's.
So to find the inverse, you swap x's and y's, basically. Yeah. The input of the function now would be the output of the inverse. Good. Kind of how inverse functions work. If you squared 2, you got 4, but you square root 4 to get 2, right? Backwards. So domain for f would be, would that be 1, 2, 3, correct? Range would be 4, 5, 6. And then domain of the inverse would be the range of the function 4, 5, 6. And this is something we should have learned in Algebra 1, maybe a little bit in Algebra 1. So just a little bit of review, right? Not too bad. And remember, f inverse would be the -1 power. Does not mean reciprocal. That means inverse function, right? Same with trig inverse functions. You'd write that -1 up there. Does not mean reciprocal. It means inverse function. Dust off the old cobwebs. Well, let's find the inverse function. And not always is the inverse a function. Do you remember how we would go about that? Yeah, there isn't a y written, but we know it's y equals, correct? And then swap x and y. X equals 2y cubed minus 1, and then solve for y. Some people might solve for x and then swap. I'm not a fan of that. I'm thinking swap x for y right away. This is the inverse right here, guys. This is the inverse. As soon as you swap x's and y's, that is the inverse. Now it's just more convenient to solve for y, right? Add 1, divide by 2, x plus 1 over 2 equals y cubed. And then cubed root, y equals the cubed root then of x plus 1 over 2. Now, hopefully, if this is a function, if this original function is 1-to-1, remember what that means? Passing the horizontal line test. If this is true, if this is a 1-to-1 function, that means the inverse is a function. So then we could write f inverse and relate it back to the original function. Okay, I'm sure you guys did that. Most of you guys did your homework on that, so you remember it. All right, show that f and f inverse are inverses using the function composition rule. Well, if you guys recall, using function composition rule, if you substitute the inverse into the function and simplify, you should get x. Similarly, when you substitute the function into the inverse, you should get x. In the function composition rule, to prove that two functions are inverses, you'd have to do both of these, right? That means that each function undoes the other one. And for all intents and purposes, I'm sure you guys have done that before, right? Maybe we can just set up one of them, maybe the first one. Substitute the inverse into the function. Well, that would be 2 times the cubed root of x plus 1 over 2 squared minus 1. That better be equal to x, right? And if we're going to prove these two were inverses, we'd set that up, simplify the left side, and show that the left side was equal to x. Similarly, but backwards, you substitute the function into the inverse and reduce the left side down to x to show that it, and those two were indeed inverses. You guys remember doing that a little bit? Good news is, like, the AP test is not going to test us on this at all, so I'm not going to worry about too much, but just relating the function with the inverse. Okay. Pop quiz. If f of 1 equals 5, what does f inverse of 5 equal? 1. Right? So if this is your xy, 1, 5 for the function, then 5, 1 is true for the inverse, right? So the inverse function you evaluate at the y is the x for the regular function, right? That's going to be important later for us. So let's keep this idea in mind. Well, I'm going to show you guys pretty much 3 ways to find the derivative of the inverse. One of them is called method 1, which is just muscling your way through it. And then we have 2 variations on method 2. Okay? Let's start out with method 1. So find the derivative of an inverse function. So the derivative of an inverse. So I have an inverse function, and I'm finding the derivative. So d dx out in front, or just a prime out there, right? There's a couple different ways we could write this. So we're finding the derivative of an inverse. This method, method 1, will be used when the inverse is actually easy to generate, when we can actually find the inverse function, that is. All right, so if we had x squared as our function for x is greater than 0 or equal to 0, or it wouldn't be a function, right? Because you'd have that bottom loop underneath there. Find the derivative of f inverse, so the derivative of the inverse at x equals 4. One way they try and confuse us, they'd say, find the slope of the tangent line of the inverse of x, or inverse of f, at x equals 4. It's the same thing we're doing, right? So, method 1, number 1, find the inverse. So, for number 1, we'd have y equals x squared. Swap x and y's. X equals y squared. Solve for y. Now, typically it's plus or minus, correct? But we know y has to be positive because it says x is positive. The input of the original function has to be positive, therefore the output of the inverse needs to be positive. That's why we're only using positive square root. Okay. Step 2, take the derivative. So we need to find the derivative of this. D dx of y equals x to the half. Parentheses around everything, showing that we're taking the derivative. And this is the derivative of the inverse. Okay, this is your inverse function. We are finding the derivative of the inverse. Okay, so dy dx 1/2 x, that'd be negative half, right? Which would be 1 over 2 root x. There we go. There's the derivative of the inverse. Step 3, substitute x in. So dy dx evaluated, x equals 4. 1 over 2 radical 4. That's 2. 2 times 2 is 4, so 1 over 4. Now, they could ask us to make this equation of the tangent line to the inverse of f at x equals 4. Find the inverse, find the derivative, substitute x equals 4. There's your x value, there's your slope, but people get the y value wrong all the time because they plug it into the function and not the inverse. Your y value would be 2, not 16 on this one, right? Questions on that? Okay, this method always works, right? It's kind of the muscle your way through it. It always works, and it's going to be good for easy to generate inverses. But we know calculus is not always easy, so we have method 2. And the first slide from method 2 is going to be like the first problem, a little more intense, but after that we streamline it a bit. Method 2, when finding the inverse is difficult. What type of function would be difficult to find the inverse of? If you have more than one x value over here. Because the first step in finding the inverse would be swapping x's and y's. Now all of a sudden you have a whole bunch of y's over here you have to solve for. Good luck. Have fun with that. So we have method 2. Step 1, find the inverse by swapping x and y. And at this time I wouldn't solve for y. Step 2, find the derivative implicitly. Step 3, solve for dy dx. It will be in terms of y. 4, replace x into the inverse in step 1. And solve for y. Step 5, plug that y value into dy dx. Why are we plugging that y value into dy dx? We good? Move on a little bit? All right, get your calculators ready just in case we might need them. Find the derivative. Now, sorry, you guys have this kind of written down on your paper. I'm going to have to scroll up and down a little bit for the process. Step 1. Again, we're finding the derivative of the inverse at an x value. Step 1. Let's find the inverse by swapping x's and y's. Okay. Well, that would be, are you guys okay if I just assume this is y and swap it right away? X equals y cubed minus 4y squared plus 7y minus 1. Be careful with your x's and y's. Don't be like me and start being sloppy. There we go. Now, this is the inverse function, right? Correct? That is the inverse. Like f of 1 equals y, but f of y equals 1, right? In this particular case, here, and then f inverse of y, f inverse of y equals 1. Okay? F inverse of y equals 1. That's why we're going to be putting a 1 over here later. Okay, step 2, find the derivative implicitly. Step 2, find ddx. ddx both sides. Okay, the derivative of x with respect to x is just 1. Implicitly over here on the right side, okay, the derivative of y cubed with respect to x, variables don't match, so it would be 3y squared dy dx. And again, we could just say y prime, 8y dy dx, and then plus 7 dy dx, and then plus 0 dy dx, but that's 0. Okay, solve for dy dx. That's a quick factoring. Should we do an advanced move on this one? Not write it twice? Are you guys okay? So I'm going to factor this all out, right? And then divide over. This will be 1 over 3y squared minus 8y plus 7. Okay with that? That's step 3 was solve for dy dx, right? My bad. Step 3. We'll put it right here. Step 3. Okay, what was step 4? Let's go back up here. Replace x into the inverse step 1 and solve for y. Okay, here's some place where people get confused. Well, guys, our derivative, this is the derivative of the inverse right here, right? It is in terms of y, right? They gave us an x, and so we got to find that value to be able to plug it in here, okay? So step 4, 1 equals y cubed minus 4y squared plus 7y minus 1. Now, again, good luck solving this. Let's use your calculator. Let's either subtract 1 to the other side and find your root, or find where these two lines intersect. I like finding the intersection because I don't have to go like left bound, right bound. I just hit intersect, enter, 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 done. Unless there's more than one intersection. This can be a decimal approximation, so you're going to have to store this in your calculator then. Remember how to store the value? Bottom left, after you get out of the graph, store, and then like A or B or whatever. I wouldn't store it as X. I'll store it as A or B or something. What are you guys getting approximately? 349 and some change? 0.349378081, something like that. Now again, we are STO arrow, and I'm storing as an A, right? Because I don't want to have to retype this anymore. Because why? What does step 5 say? Take this value and plug it into your derivative, right? So what I'm going to do in my calculator, I'm going to go 1 over 3a squared minus 8a plus 7. Remember to have parentheses around the entire bottom though. We're evaluating the derivative at that y value now. And when you have a confident answer, 218 or 219 truncate around, right? Now, this is a little cumbersome, a little clunky, isn't it? Okay. Why are we taking a y value? Why are we doing this? Well, that's just the way things kind of worked out. Everybody able to get it? Make sure you can. Now, let's work on streamlining this a little bit. Okay. Method 2 can be streamlined a little bit. Now, to do that, what we're going to do is we're going to start with one of the pieces of the definition or the function composition rule for inverses. Let's take one of these pieces and let's take the derivative. We're going to develop something to streamline this process a little bit. So let's take the derivative of this piece. So I'm taking the derivative of this equation. Now, the left side, this is a composite function, right? So that'd be the derivative of the outside at the inside times the derivative of the inside. Well, that would be f inverse of x prime, right? And then the derivative of x is 1. Well, looky here, guys. We have the derivative of the inverse right here. If we divide by this mess, we will have a formula for how to find the derivative of the inverse. The derivative evaluated at the inverse. And sometimes they will write it as f inverse derivative x. That's the same thing. Now think about this, guys. If I go backwards for one quick second, 1 over the derivative evaluated at the inverse, That's right here. Okay, we're going to streamline it a little bit though. Again, if f of 2 equals 7, what does f inverse of 7 equal? 2. So they're going to want the inverse evaluated at 7. Well, we're going to have to figure out what x value gives us 7. And that's what we did over here. Right here, when we set this equal to 1 and solved. Actually, I should say it right here. We'll be doing that. Okay, so let's try this process, the streamlined method 2, on a new problem. Find the derivative of the inverse, f of x equals x cubed minus 1 at x equals 26. Well, let's use this new streamlined formula, this new toy. F inverse derivative at x 1 over the derivative evaluated at the inverse. All right, for the first time, I'll substitute 26 in, okay, to maybe help clarify some things. F inverse derivative at 26. So the derivative of the inverse evaluated at 26 equals 1 over the derivative evaluated at the inverse 26. Now here's the deal. If we want to find the inverse at 26, if we want to find that answer, what do we have to do? We have to figure out what value evaluated at the function equals 26, right? Okay, so that's our first task, guys, to figure out this quantity. To do that, well, set the function equal to 26, solve for x. Add 1 to both sides, 27 equals x cubed. Oh, that's not bad. What's the cubed root of 27? 3. So f of 3 equals 26. That means f inverse of 26 equals 3. So right here goes 3. 1 over f prime of 3. What? All you're telling me is we have to take 1 over and find the derivative evaluated at 3? Yeah. Find the derivative now. So it'll be what, 3x squared? Find when the derivative, or evaluate the derivative at 3. 9 times 3, 27. So this is just 1 over 27. There we go. This would be the slope of the tangent line of f, the inverse of f, at x equals 26. Composite function, use a chain rule, guys. Bring it back to calculus. All right. All right, let's use our new streamlined method 2 for this. Okay, we're going to find the derivative of the inverse at x equals 2. Let's do that. So the derivative of the inverse of x, again, is 1 over the derivative evaluated at the inverse. And again, if I plugged in 2, just for fun, I'll write it again. Hopefully maybe to clarify some things. It's kind of tricky, this inverse business. Especially if I start writing inverse instead of derivatives. That'd be really tricky. Again, f inverse of 2 equals we don't know. That means that f of we don't know equals 2. That's kind of the main key. We got to be able to substitute right here. We got to figure out when is the function equal to. So 2 equals x cubed plus 2x minus 1. I don't know, either minus subtract 2 and solve, or do what I need to do. Maybe use a calculator, see what we got here. Huh? Is 1? So 1 plus 2 minus 1 is 2. That'll work. So f inverse of 2 equals 1. So find the derivative and evaluate the derivative at 1 then. Okay, the derivative would be y prime equals 3x squared plus 2. Y prime of 1, 5. So the derivative of the inverse at x equals 2 is 1/5. This is streamlined quite a bit, isn't it? Notice, we're finding the inverse, we're finding the derivative, we're using them together. This is a lot easier. If you can remember this, the derivative of the inverse is 1 over the derivative. Evaluate at the inverse. Here's a big key step, and go from there. Okay, let's try this one for fun. Okay, so if this is 2, if f inverse of 2 equals I don't know, then f of I don't know equals 2. Set the function equal to 2. This is definitely a storing value, I believe. So x is approximately equal to, are we getting 737 for this one?
Yeah.
And some change. If I'm going to store this as a, that means I'm going to have 1 over f of a, f prime of a. Well, f prime is 3x squared minus 4x plus 5. Substitute a into this, and all you have to do is type in your calculator, guys. 3a squared minus 4a plus 5. Take 1 divided by second answer, and you got it. And we're storing this value because we do not want to round until the very end. 272 if you're rounding, 271 if you're truncating. Is that right?